All right, section 4.2. So sigma notation. This should be familiar, even if you've never seen it in math. You hopefully have seen it in like Excel. It basically means the sum of the terms, where I is the index of the summation, ace of I is the ith term of the summation, and the upper and lower bounds of the summation are n and 1. So basically, you're adding up terms from the first term, which is notated down here, to the last term, which is notated up here. And they give you some examples. If I starts at 1 and ends at 6 and you just have I, you're going to add 1, 2, 3, 4, 5, 6. If I starts at 0 and ends at 5 and your summation is I plus 1, then you're literally going to plug in a 0, a 1, a 2, a 3, a 4, a 5, and you'll get 1, 2, 3, 4, 5, 6 here. If your summation is j squared and j starts at 3 and goes to 7, you're going to say 3 squared plus 4 squared plus, so on and so forth. This guy tells you what you're doing with the numbers. This tells you the numbers you're going from. You'll notice that it is whole numbers, right? So we're not doing 1, 1.1, 1.2, we're doing our whole numbers here, from the first number to the last number, or from the lower bound to the upper bound. And you're literally just adding them. The last one is important because we're going to actually be doing stuff like this. The function of x, the change in x, and you literally just plug in your numbers. And so there are some summations that you need to memorize, and here they are. So if you have a summation from 1 to n of just a constant, you just have to take that constant times your upper bound. And that's what your summation will be. Because you're literally just, if it said the summation of 1 to 5 of 3, well, that means your first term would be 3, your second term would be 3, your third term would be 3. All 5 terms would be 3. So you're adding 3 5 times, which is just 5 times 3. So if it's just a constant, it's just the constant times your upper bound. Gauss is credited with number 2. Little Gauss, as the story goes, the teacher got aggravated with the class. Not that that would ever happen. And she told them to add the numbers from 1 to 100. Little Gauss figured out that they came in patterns. 1 and 100 were 101. 2 and 99 were 101. 3 and 98 were 101. 4 and 97 were 101. And he realized he would have 50 of those. So you take the last upper bound plus 1, and you multiply it by half of the number that you're going to have. So he said 50 times 101 is 5,050. That is 1 to 100 added up. And he went back to his teacher within a few minutes and surprised her with the right answer because he had figured out the pattern. So if it's just I, like 1 to 100 added up, you take your upper bound, however many you're adding up, multiply it by that plus 1, and divide the whole thing by 2. The next one is I squared, n plus 1, 2n plus 1, all over 6. And then 4 reminds me of 2. I cubed actually reminds me of 2. It's just n squared, n plus 1 squared, and then 2 squared on the bottom, 4 on the bottom. So it's like you take I and you square it. Square each piece. Isn't that what it looks like? So I and I cubed are very similar. The one that's kind of off of its own is I squared. So let's see how this works. Example 2, evaluating a sum. So you really need to memorize those because you're going to use them. We're going to do some limit theory with them, and then we're going to move into not using them in antiderivatives so much. But you need to remember where it came from, and you need to use it for the next process we're about to do. So evaluating. They want I from 1 to n, and my function here is I plus 1 over n squared. All right, n is my upper bound, all right? They want me to do that for 10, 100, 1,000, and 10,000. Now, I don't know about you, but I do not want to add the numbers from 1 to 10 even for I plus 1 over n squared, okay? So I definitely don't want to do it for 10,000. So we're going to reduce this guy to just something with n, where we could just plug in the 10, the 100, the 1,000, and the 10,000. So when I have the n here, like this, I can pull him out in front. So I can say 1 over n squared, because n is just a number. And then I have my summation from I equals 1 to n. And I'm left with I plus 1. All right? And now what I can do is I can go back to these guys, and I can substitute my notation for what the actual summation is. So basically, this represents the summation of I along with the summation of 1. So the summation of I and the summation of 1. I is up here. We got that summation. And 1 is just a constant, so we have that summation. And so we're going to use those two, and we're going to replace the summation of I and the summation of 1 with what we know them to be. Okay? And so when we do that, we get the 1 over n squared. He's going to stay there. We're going to replace the I with my n plus 1 over 2. That's what I is, right? And we're going to replace my 1 with 1 times n. Basically simplifying your rules of fractions and all. So if I were to multiply, just distribute it through, I get n, I'm going to distribute the top, n squared plus 1, n, right, all over, and then I'm going to multiply these guys, 2n squared, plus n over n squared. So far, so good. All right, and you can simplify this. You can actually add, since you have the common denominator there, you can actually just do n squared plus 2n, right? And we multiply this guy to get this common denominator by 2, right? So we're going to say 3n. I did it in my head and did not add my other n. All over n squared. So common denominator, I'll write it neatly because I'm not really writing it neatly there. So we have n squared plus 3n over n squared. You can reduce it, so you can reduce an n out of everything just like you would. Reduce there, reduce there, reduce there. And I get n plus 3 over n. Much easier now to go back and plug these guys in to get the summation. All I have to do is plug these in. 10 plus 3 over 10. 100 plus 3 over 10, 100. 1,000 plus 3 over 1,000. And so all of a sudden I can get a much easier summation for those versus plugging them in individually. So if you put the summations in first and then simplify, you can do it then for any number, the summation of any of the numbers from 1 to whatever number they give you. All right? So we did talk about this at the beginning of the year. This is one of the problems that came about because of your pre-cal world. And in pre-cal world, if you have a rectangle, finding out the area, we got this, base times height, you know. But in the calculus world, we don't have these set figures. We have these curves. And so we start running into this problem of then how do we find the area then of something that isn't the norm when it comes to a geometric figure. And so if I want to find the volume or the area rather of this guy right here, I have this odd shape that I don't have a geometry equation for him at all. I don't have one. And so this causes a problem. And so what we do is then we go back to what we know. And we said, well, what I do know how to do is calculate the volume of a rectangle. So if I want to calculate this volume, then I can create rectangles. And so that's what they've done here. We have the function. The function represents that curve. And we want to know the area of the curve between 0, x equals 0, and x equals 2, those two lines there. And so this is where we get, you know, my starting and ending point, 0 and 2. And so what we then recognize is, well, there's going to be 5 rectangles. And I can calculate the base and height of each of those. They've given you the two options here. I can have, using my right side as my endpoints, and so that gives me under the curve there. Or my left side here gives me above the curve, you can see. So on the left-hand side, while I'm using my right endpoints, I really should have flip-flopped those pictures, but that's how they are. So if I'm going to move, we'll say right and left because it's going to be confusing to me even. So if I use my right endpoints and I use this as an endpoint, I create this rectangle. This as an endpoint creates this one, so on and so forth. You notice I have this little bit here. If I use the left-hand side and create this rectangle and the left endpoints, I create those and I have this excess. What I do know for sure is that it's going to fall somewhere in between these two. All right? If I calculate my right endpoints, that's going to be my smaller number. If I calculate my left endpoints, that's going to be my larger number here for this guy. And I know the actual amount will be somewhere in between. And we'll talk about increasing those rectangles, which is kind of what we talked about at the beginning of the year. So the first thing you want to think about is then what is my base and what is my height? And so we're going to talk about this one first. We'll move him out of the way. Scooch over. All right, we're going to talk about this one first. If I want to know my width, I am going to take my entire width and divide it by how many rectangles I have, right? So if I go my entire width and divide it by how many rectangles I have, then that's going to tell me what I actually have. My entire width is 2, right? Yes, from 0 to 2. So my entire width is 2, and I have 5 rectangles. So that should be the width of each rectangle, right? 2/5, 2/5, 2/5, 2/5, 2/5, right? Make sense? Height. Height is going to forever change depending on where I am. The height of this first guy here, that's going to be up here. Well, how do I find this y value if I have this x value? You have the x value. How do you find the y value? You plug it in. Another way to write that is just f of my y value, right? Yes? Then I'm going to add that to base times, if I can write, that'd be better, base times my next height. Yes? Makes sense? So on and so forth for all 5 rectangles. Okay? There's another way to write that. I could say, well, 2/5 is always going to be my width, right? My height is going to be dependent on which one I'm talking about. So I could actually write it like this, 2/5 times I. Yes?
So what just happened here?
So I'm taking these and I'm plugging them in, right? But instead of plugging in, I could say, well, I could just use my summation, right? And instead of plugging them all in, I could say, well, this is my first one. This is my second one. My third one would be 2/5 times 3. My fourth one would be 2/5 times 4. My fifth one would be 2/5 times 5. 1, 2, 3, 4, 5, right? And so if I do it that way, I could just say, well, that goes from my first one to my fifth one. Make sense? Summation, all right? And so when that happens, then you can actually plug it into your function. So then I'm gonna have the summation here of a function going on. So let's look at the function. The function is up here, all right? So I'm gonna say, well, I still have the summation from my first number to my second number. My width is not gonna change. It is 2/5. The width of each one of those rectangles is the same width, 2/5. And instead of f of this guy right here, I'm gonna plug that guy in. So I'm gonna say that's times 2i over 5 squared plus 5. Because that is my function. And I just plugged this guy in, which was my x value. My negative x squared plus 5. So far, so good? And then I just solve for it. That seems easier said than done, but we have a summation formula, okay? When you have a summation formula, this guy can go on the outside. It's just a number, right? So I can pull that 2/5 on the outside and multiply it in at the end if I want to. But what I need to do is I need to figure out what my summation is. And I can replace that I with the summation formula. And so here, I'm going to actually just do the math. Seems easier said than done. All right, we have this 2/5. All right, I have negative, and I'm going to square this guy, right? So 4 over 25, yes, I squared plus 5. So far, so good? So what is I squared?
I squared is
And so that's what I'm going to plug in there. And so I can replace my summation. So I can replace my summation formula for I squared with what that formula actually is. All right, and that's what I'm going to do there. I'm going to say 2/5 times negative 4 over 25 n plus 1, 2n plus 1 over 6. All right, and what about this constant here? How is he fixed with the summation formula?
it's just your constant times n.
Yep, 5n. Now you can simplify that in all, which is fine. And you're gonna have to when we go to limit formula. But at this point, if you don't want to simplify, you can literally plug your 5 in. And so what happens when you plug a 5 in? You do. 6.48.
Okay, yeah. Just making sure.
Yeah, you should get 6.48 when you plug a 5 in. So 5 times 6 times 11 divided by 6 times 4 divided by 25. That's a negative. Plus 25 times 2/5. And you get the answer. And so when you do all of this little guy here, you get 6.48. All right? That's my right endpoints. My right endpoints, all right? If I were to do this with my left endpoints, instead of using I, okay, I'm going to use I minus 1. All right, and I'll explain why. So let's bring this guy back up here. All right, we'll compare these two so you can see them. All right, if I'm using my left endpoints, then what I'm plugging in is not going to be 1 times 2/5. It's going to be whatever my place value is minus 1. Because if I'm using my left endpoints, I'm not going to use my first place. I'm going to use my first place minus 1 because it's the left one. And here I'm not going to use my second place. I'm going to use that minus 1. And I'm not going to use my second one here. I'm going to use my second one minus 1 because I'm using my left ones. And so all of a sudden you get I minus 1 plugged in instead of I. And that's the only difference. When you plug it in, you get 8.08. which seems, all right. And so this is what we got when we plugged in the smaller one. This is what we get when we plug in the left-handed side ones there. So we can say without a shadow of a doubt, well, somewhere between 6.8 and 8.08 is my actual one. All right. Now, that's not very close. It's not a very close and accurate area evaluation, do you think? I mean, I'm like 1.5 off on only an 8-point scale. All right. It's not like I'm 1.5 off and it goes from 0 to 1,000 here. It's from 6.48 to, I mean, that's a pretty broad range considering those are pretty small numbers. Okay. And so if I were to even be 0.0 something off, then it's a lot closer. But in this case, I'm really far off. And so what you'll notice with these is what we've kind of said before. What happens is five rectangles is not very many, and you leave pretty large gaps in there. And so if I increased it, and you can see I have more here, then my gaps are smaller, but I still have gaps. And so I want this actual area, and I have this gap problem. And so we have lower sum and upper sum, which is what we just calculated. The lower sum being the smaller one, the upper sum being the larger one. Inscribed rectangles versus circumscribed, if you remember your geometric terms from long ago. All right. And so we have this problem that keeps coming up. Well, then maybe I can do 10 rectangles, okay? Or maybe I can do 20 rectangles. But the more rectangles you have, the closer you're going to get to the actual sum of this guy. And so this is where limit theory comes in. If you look at this, there we go. Limit theory comes in when you can say, okay, here's the deal. I don't want to do 20 rectangles. I'm still going to be off. I want to do an infinite number of rectangles. Right? That sounds great. So we do the summation, and then we put this little guy in front of it. And we're going to say, okay, I'm going to do the summation like I've been doing. But instead of plugging in 5 rectangles or 10 rectangles or 15 rectangles, I'm going to say, well, I want it as n approaches infinity. And calculus lets us do that. And if we can find what happens as n approaches infinity, then all of a sudden we actually have the area under the curve. And we've reached it. And so as long as a limit exists for what they have given you, this is what you can do. And so here's the actual definition. And I believe the definition is on page 259 here. Let f be continuous and a non-negative on the interval. Non-negative is important. We'll talk about that later. The area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b. The area is the limit as n approaches infinity of the summation of I equals 1 to n of f of ci delta x. All right, this just means how it changes divided by the number that we're going to have, however many that is, n. And then we're going to plug that into C. All right, and so really quickly, next example here, all right, we're going to look at what happens. All right, for this one it says find the area of the region bounded by the graph f of x equals x cubed, the x-axis and the vertical lines x equals 0 and x equals 1. All right, and so for this one, we are going to take kind of what we've done before, and we're going to find out. So the first thing we need to figure out is delta x. So if I look at my formula here, my area is the limit as n approaches infinity of the summation from 1 to n. And I don't know what n is, but we're going to do as it approaches infinity. So we're going to leave it as an n, delta x, right? Now, in order to do this, I need to find my delta x, all right? So the first thing we need to know is what is delta x? They actually explained this prior, but we're going to talk about it now. Delta x are my two endpoints that I'm talking about. The ending point, if they've given me an interval, minus the beginning point divided by the number of rectangles. In this case, I'm as it approaches infinity, all right? So I'm going to leave it as an n because we'll wait for the limit theory at the end. So delta x is always going to be that guy. All right. C of I. So what happens with C of I, what we're going to actually plug in here, is going to be basically ends up being my delta x times I. So whatever you have here, we're going to take him and we're going to multiply him by I. So for this one, they want me to go from 0 to 1. That's my A and B. All right. So if I'm going to find delta x here, delta x is going to be 1 minus 0 over n, which gives me 1 over n. My C of I then is going to be I over n. And so now we're going to plug it into the function. So you go up here and you look at your function. They've given us this function. All right. So we're going to say, well, in order then to find my summation, I'm going to say the limit as n approaches infinity of the summation from I, 1 to n, f of C of I. So I'm going to plug in this guy into my function. My function is x cubed. Instead of x cubed, I'm going to write I over n cubed, x cubed. And I'm going to multiply that. That's your height times your width, your delta x. So this is f C of I right here. And this is delta x, which we found to be 1 over n. And now we need to actually do it. So we need to actually cube this guy. All right? So I have limit as n approaches infinity. My summation little guy there, because I haven't replaced him yet. This is I cubed over n cubed times 1 over n. Right? My n is a number. Okay, so think of it as like 1/2 if you have to. So I could simplify this to be I cubed over n to the 4th, right? Now what I want you to know about this is your 1 over n to the 4th can be yanked out into the front of this. So I could say 1 over n to the 4th out here, and then I can just do my summation of my I cubed. So I can pull that 1 out of n to the 4th in the front, okay? I still have my limit theory, so my limit's still going on here. All right, and now I'm going to do my I cubed. What is my I cubed?
N squared times n plus 1 over 4.
Squared over 4. All right. Did everybody see that? And then you need to simplify it. Before you can do your limit as n approaches infinity, you have to simplify this guy right here. All right. So that's what we're going to do. So this simplifies, and some of you, all right, on your quiz didn't. All right. So you want to make sure that you FOIL it. So I'm going to leave this 1 over n to the 4th right here. This is going to be n squared. This FOILs. So we have n squared plus 2n plus 1 over 4. And you can distribute him. All right. So we're still doing limit. All right. And we have, and I'm just going to put all of it over n to the 4th real quick. So I'm going to say n to the 4th plus 2n cubed plus n squared over 4n to the 4th. So far, so good?
So you just distributed that.
I'm going to simplify these guys here. So I have my limit as n approaches infinity. And I'm going to say n to the 4th over 4n to the 4th. Plus 2n cubed over 4n to the 4th. Plus n squared over 4n to the 4th. All right. All right. Limit as n approaches infinity. So we're going to take each one of these. What is the limit as I'm approaching infinity, I have a shortcut here. Infinity. I look at my degrees.
Oh, yeah.
The degrees are the same. So what is that limit for this one? If they're the same, I use my coefficients, right?
Yeah.
So this limit's going to be
1/4.
1/4. What about this guy? What are my degree changes here? Degree on bottom is bigger.
0.
It is 0. And what is my limit here?
0.
My answer then is 1/4. That is the area under the curve. All right, so just to walk through this, I found my delta x. I subtracted my 3 minus my 0 over my n. That's 3 over n. I multiplied that by I to get my c of I. And then I just plugged it into my formula. My delta x goes here. I plug this guy into my actual function. So I have 3i over n squared plus 1. Okay. Then I just actually squared this. So all I did from here to here is square it. So I have 9i squared over n squared. And now I'm going to replace my summations here. So I replace my I squared with n plus 1, 2n plus 1 over 6. And I replaced my constant with my constant times n. And now I'm just really doing math. So I foiled this to get the 2n cubed plus the 3n squared plus n. And I think that's all I did from green to yellow here.
Yeah.
And then I just distributed. I did show you that I reduced this when I distributed to here, but I had to distribute to both, so it only reduced here. So I distributed my 9, which is where I got my 18, my 27, and my 9. I reduced the 3 and the 6, so that's why my 2's all went on bottom. But I did have this n and n squared, so these all became n cubed. And then I also distributed the 3n to the n, so I got 3n over n. And here I just went straight to my limit, okay? These have the same degree, so it's 18 over 2, which gave me a 9. Denominator's bigger, 0. Denominator's bigger is 0. Same degree, so 3 over 1 is 3. 9 plus 3 is 12. You have to think about the fact that your whole I values shift. We're starting at 0, and so the first one is I, and the second one is I plus 1, and the third one is I plus 2, right? I'm just kind of walking along the x-axis here, trucking along. But technically what you did to find c of I, so we've always been doing, so delta x stays the same. That's b minus a over n, all right? But what happens to your c of I then, your c of I becomes your starting letter, I mean, you're starting, a, but your starting number here, plus I times delta x, which is fine when we start at 0. That's why I just was like, it's I times delta x, because we were starting at 0, okay? But when all of a sudden you shift and you're no longer starting at 0, you have to start at where you're starting from and add it to, okay? And so for this example, they want us to go from 1 to 2. And so if I want to find my delta x, that's 2 minus 1 over n, or just 1 over n. If I want to find my c of I now have to say 1 plus I over n. And that's what I will plug into my function here. Okay? So it makes for a little bit more of an interesting, because you have to actually foil it. All right? You have to actually foil it. Okay, and so if I were to do this one, it would be the same limit theory here. Limit as n approaches infinity of my summation from 1 to n. I still have to put my delta x there, 1 over n. And now I'm going to say 4 minus, and I'm going to plug this guy in, 1 plus I over n squared. Okay? And so when I do that, all this limit stuff stays the same, and the 1 over n stays the same here. But then I need to actually foil. So then I need to actually do this 4 minus, and I'm going to do 1 plus 2i over n plus I squared over n squared. I had to foil him. So just think about your foiling properties. You multiply, it's the first one squared, the 2 multiplied together and doubled. So 1 times I over n doubled, which is just 2i over n, and then I squared over n squared. And I'll rewrite that a little neater down here. So you do have to actually foil when you do that. It is a perfect square, so you can use your perfect square theories there. And then you're just going to replace your i's like you would. So I'm going to replace this I with my n plus 1 over 2. I'm going to replace this I with my n plus 1, 2n plus 1 over 6. Okay? And then of course I'm going to place this guy with my constant. You want to go ahead and, in this case, like we have this guy here. So you want to distribute that negative through and then do your replacement. So make sure you follow all your algebraic rules here. So when I'm doing this, I'm going to say distribute that negative through, which is going to give me my summation. Oh, let's actually do it with writing here. It's going to give me 4 minus 1, which gives me 3, minus 2i over n minus I squared over n squared, because I am distributing that negative here. So make sure that if you have an occasion like this, then you do that correctly. And you'll replace all of those with your i's. So you would just do that process as it is, as tedious as it may be. You would have your 1 over n out here. You would replace this with 3n. You would replace this guy with, and you can just pull the 2n out if you want to and do n plus 1 over 2. And you want to replace this one, and you can pull the 1 over n squared out if you want to, n plus 1, 2n plus 1 over 6. Simplify and apply your limit theory. I will tell you, it's not the process of doing it. I mean, it's not the difficulty. It is the easy mistakes like distributing a negative that's going to throw you.
There's so many steps, like it's like so easy to mess up.